let's look at these questions. By reference to the definitions of gravitational potential, explain why gravitational potential is a negative quantity. So to understand or to answer these questions, so let's look at the definitions of gravitational potential. So let's look at this. We have the notes at the bottom here. Okay, so as you can see here, this is, okay, you look at 2.4 here. This is the definitions of the gravitational potential. So the gravitational potential is defined as, you can see here, the gravitational potential at the point is work done per unit mass in bringing a mass from infinity to the point. So when you look at the definitions, of course, it is where you have to understand it together with the formula of the gravitational potential, which is phi. So remember, this is called phi. This symbol is called phi. Phi, phi. Okay, so the formula of the gravitational potential is phi equal to minus gm over r. So that is the formula of the gravitational potential. And let me further explain a little bit on this gravitational potential so that when we answer that question, we can have some reasonable or have some understanding on why we have to answer in that way. So now let's see here. If the formula is phi equal to minus gm over r, and let's say I am going to draw out the graph of phi versus r. So I'm going to draw out a graph of phi versus r. So in this situation, you have to use your mathematics knowledge to take it. So first, this is a reciprocal graph. So we have to know that it's a reciprocal graph because r stays at the denominator. So the graph looks like this. Okay, so it looks like this and like that. Okay, so the objects which creates gravitational potential stay here. So let's say I use blue color. The objects that creates gravitational potential is here. Okay, so this is the object with mass m. Okay, so now when you know the graph is like this, so we can take it mathematically in this way. So first of all, if you look at the graph, if the r is very big, which refer to this side, okay, as you can see here, when the r is very big, of course the meaning of r here is the distance between two masses with two objects with mass. Okay, so the distance between two objects with mass, so that is r. Okay, let me draw out to let you imagine on this. So if you have two objects, let's say this is object with mass capital M, and let's say this is object with mass small letter m. So the r is actually the distance between two objects. Okay, so as you can see there, you see what I do here is the r is from the center of mass of one object to the center of mass to the other object. Okay, so the r is the distance in between. Okay, now let's come back to this graph and let us understand it. So what we can do here is, you can see, let's say this blue color object has mass m, okay, has mass m, so which refer to these objects. And imagine that this is, let's say, okay, so to make us easier, I give an example in this way. So imagine that this is our earth, okay, our earth that we stay in, and let's say this is a rock which is approaching the earth, okay, approaching the earth. So initially the rock is very far away from the earth, let's say, okay, the rock is very far away from the earth. Of course, logically we can think of this rock is hardly attracted by the earth because it is too far away. So this is where we understand it at this part. When the rock is very far away, we can't expect the earth to attract the rock. So that's why the gravitational potential is zero when the distance is infinity. So imagine now the rock is getting closer and closer to the earth. So in that situation, when it is close enough, the earth is able to attract the rock. Okay, so it's able because they are close enough, and to represent that, you can see it here. So when the rock is getting closer and closer, the graph is getting more and more negative, okay, so it comes to the important point now. It's getting more and more negative. So more and more negative means, you have to know that the negative here means attraction's force. The gravitational force is always attractive, so it is represented by negative sign. Okay, so when the negative is getting more and more, so in other words, when it is getting more and more negative, it means the attractions of the rock and the earth is getting stronger and stronger. So it makes sense if there is a negative in the formula. So we must have a negative in the formula so that everything makes sense. Okay, so when the rock is approaching the earth, the attraction is getting stronger and stronger. So the only way to make these represented is by having a formula with a negative sign over there, so that the graph goes down. Okay, so and it has 0 at infinity, as you can see here, 0 at infinity, and keep going down when it approaches object M. Okay, so I hope you get some idea, and now let's see how we understand, how we answer the questions. So let's take a look here. Come back to the question again. Okay, here. By reference to the definitions of gravitational potential, okay, so we already look at the definitions, which is the work done per unit mass in bringing a mass from infinity to the point, okay, to the point, okay, to a particular point. That is the definition of gravitational potential. Okay, so explain why gravitational potential is a negative quantity. Okay, so how are we going to answer the questions? So first of all, you have to say, first point, there are 2 points here, as you can see. So first you say gravitational potential at infinity is 0. So this is the first point. As you can see from the graph that I explained just now, which is like this and like that. Okay, so this is r and this is phi. So we are talking about this part. Gravitational potential, the phi at infinity. At infinity means when r is very big, so the phi is very close to 0. So that's why this is the first point. Okay, so it's based on the formula as well. So remember that. Okay, where our formula is, okay, I write the formula down. Phi is minus gm over r. Okay, so the negative is there. Okay, so and the graph is the reciprocal graph. Now let's move on. So what else are we going to say? So let's take a look first to get the second point. So okay, we have to mention something like this. So you have to say gravitational force is attractive. So this word attractive is of particular importance, is the key word. So the negative sign, okay, the negative sign, as you can see in the formula, the negative sign means attraction force. Okay, attraction force. So you have to mention this as the keyword. So gravitational force is attractive. So we continue. So that work is done as object moves from infinity to a point. Okay, so the second point, there are two ways to take it. The first thing is attractive. Attractive means it has to be negative for the formula, or in terms of graph, it has to goes down, because like what I said, it goes down means that the attractive force is getting stronger and stronger. So when, like what I said just now, the example that I gave just now, when the rock is approaching the earth, that the earth and the rock can start attracting each other when they are close enough. So that's why negative has to be there so that everything can be represented accordingly. Okay, so this is the second point. Now let's look at B then. Let's look at B. Two stars A and B have their surface separated by a distance of 1.4 times 10 to the power of 12 meter, as illustrated in figure 1.1. So as you can see here, they are separated by 1.4 times 10 to the power of 12 meter. Okay, so let's continue the question first. Point P lies on the line joining the centers. Point P, as you can see here, lies on the line joining the centers of the two stars. So as you can see, this is the center of the star A, and this is the center of star B. So there is a line that join up the center, and point P is just somewhere on the line. The distance x of point P from the surface of star A may be varied. Okay, so that means the x can change. Okay, and then which means point P can move to different points on the line. Okay, so the variation with distance x of the gravitational potential phi at point P is shown in figure 1.2. So this is the variations of gravitational potential phi in between two stars. So okay, before we look at the following parts of the questions, so let's think about the graph. Why the graph is like that? So let us understand it so that we understand the questions better. Now let's take a look on the basic that I explained just now. Phi versus r, the graph is like this. Okay, the graph is like this. So but how come when it come to this situation the graph looks different from that graph? Okay, so we have to understand it, why this graph is different from these. So let's think about this. Okay, so I can explain it in this way. So first of all, when you look at star A alone, okay, when you look at star A alone, the basic graph can be applied on star A in this way. So you look at the graph. Okay, I draw it here. Okay, so it's going to be like this. Oops. Okay, so let me draw out. Okay, I need a bigger space to draw this out. Let's say I do it here. Okay, so it's kind of limited space over there. Okay, this is star A. This is the graph. Phi versus R. Okay, phi versus R. So I purposely make it long enough so that you can see something. Okay, so let me pull down a bit. And okay, so we don't focus on this side because there is nothing to discuss about on, I mean, okay, look, let's look at the pointer. We don't focus on this side because there's nothing to discuss about at this side, as our main concern is this side. Okay, so based on our basic concept, as you can see here, okay, our basic graph, based on this graph, the graph should look in that way. So let me do it here in red color. So the graph should look like this. Okay, so this is for star A. So this side, of course, you have the, okay, I have to make it a bit more accurate. So let me add line like this. Okay, so like this, a dotted line. Okay, so which means okay, the graph will be like this. They keep going down in that way. Okay, so yeah, you just compare with the graph that I explained just now. As you can see on the surface, it just keep going down. Okay, just keep going down. So now let's move on. Okay, they're supposed to have graph at the other side, but like what I said, it is not our concern. So I just put it in dotted line. Okay, we ignore. I mean, the thing is there. It's just that we don't want to discuss about that. Okay, now let's look at star B. Star B. This is star B. Okay, star B has. I mean, the basic concept of this graph can be applied on star B as well. On star B, okay, on star B. So let's say star B is somewhere over here, a smaller star. Okay, so the center of mass. Okay, so this is star B. Okay, so our graph of phi versus r will be like this. Okay, this is where I pull down from the surface of the star. Okay, so okay, now let's look at the basic graph again. So our basic graph is like this, it's like this. So this time I'm going to use this way. Okay, this, the left hand side, the graph on the left. So I ignore the graph on the right because we are not going to discuss this. Okay, we are not going to discuss the phi on the right hand side of star B. There is nothing to discuss. So we want to care about the left hand side of star B. So let's take a look here. The left hand side of star B. So I will put it in blue color. The left hand side of star B. So as you can see, the graph is going to be like this. Okay, as in blue color. Okay, now how are we going to understand, or how are we going to take this graph? So there's a concept here. Okay, I mean this graph. So the graph that is given in the question. Okay, so in fact this graph is actually the overall gravitational potential of the two stars. As you can see, the red color graph here and the blue color graph here, which create gravitational potential in between the two stars. So the overall result is hence like this, the overall result. Okay, so how are we going to take it? So we actually adding up. So we're adding up. We're adding up the values of the blue graph and the red graph. So imagine if you have a value which is very negative, add up with a value which is very close to zero, the result is, of course, a negative. Okay, it's a negative. So likewise at this particular point, so okay, maybe I draw out first. So that's why this one, I mean here negative plus zero, so we end up with negative. So we end up with negative. So it's something like this in black color, something like this. Okay, then the graph will keep going up, and then it will go down. Okay, it will go down. Maybe I put like this, so that is more reasonable. Negative. So if you look at the black color graph, here, so this graph is the graph given in the question. So what is the reasons over here? You just add up the two value, you know. So for example, let's say this value is let's say roughly -2, -2. So the the red graph takes -2, the blue graph takes -2, so the total is -4. So as you can see here, okay, this point -4, okay, that is roughly the idea on why we have this graph. Okay, let's say one more part. Okay, it's not our main concern, so we just want to understand a little bit on why the graph looks like that. It is the overall effect of two stars that creates gravitational potential in between them. Okay, the overall outcomes. So let's say one more example. Let's say, okay, why the graph here is going down. Okay, basically because of the overall effect of the star A and star B. So imagine this value is a negative value, let's say -10, this is -1. So the outcome is you add up, you know, so -10 plus -1, -11, for example. Okay, so it's that kind of concept. Okay, so we understand, hopefully you know why the graph is like that, and now let's move on with the questions. Okay, move on. So what we can see on the next part of the questions is like this. Okay, now let's see the next part. So this graph is given, and we have to make use of this graph, and you have to know what happened, or at least a little bit on why the graph is like that. Okay, so now let's move on to the next part first. Okay, you have the third object. This is a more advanced question compared to the basic concept that we mentioned just now. Okay, so this is the third object. Let's take a look first. A rock of mass 180 kg move along the line joining the centers of the two stars. From star A towards star B. Okay, so let's look at that. Okay, I put it in red color again. You can look at the figure 1.1. So I'm going to put a red point here, showing that this is the rock of mass. This is the rock of mass 180 kg. So this rock is in between star A and star B. So this rock is experiencing gravitational potential as like this. Okay, as like this. Okay, so initially is very negative. That means attraction is very strong. Okay, attraction is very strong. What kind of attraction? Is attraction by star A, you know, because it is very close to star A at this particular point. So which means here, okay, here at this particular point, it is attracted strongly by star A. Okay, let me write down. Okay, let me write down so that you can follow on what am I trying to say here. So at this point, it is attract strongly by star A. Okay, so I mean the rock is attract strongly by star A, and that's why you can see this value is kind of negative. So the idea is the more negative the gravitational potential, the stronger the attractions. Okay, so now let's come back to the question. The rock moved towards star B. Okay, imagine that I put an arrow here on figure 1.1. The rock is moving towards star B. Okay, so let us understand a little bit on what happens here based on the graph. So based on the graph, the attraction is getting weaker and weaker when rock A is moving further and further away from star A. Okay, so it has the weakest attraction somewhere around here, weakest attraction. In terms of figure 1.1 is somewhere around here, so where it is a point that is kind of far away from star A and far away from star B as well, so the attraction is the weakest as shown here. And the rock continue to move all the way, as you can see they move all the way to star B. So when they are getting closer and closer to star B, right, so like what I said, the star B start attracting the rock more and more, okay, and hence as you can see in the graph keeps going down, getting more and more negative in terms of phi, the gravitational potential, meaning that the attraction is getting stronger and stronger when the rock approaches star B. Okay, now we look at part 1. Use data from figure 1.2. Figure 1.2, that means they expect you to know this graph and know what happens, and now you have to apply the concept. Okay, calculate the change in kinetic energy of the rock when it moves from the point where x equal to 0.1 times 10 to the power of 12 to the point where x equal to 1.2 times 10 to the power of 12. So that means here, this is 0.1 times 10 to the power of 12 at this point, and go all the way to here. This is 1.2 times 10 to the power of 12. Okay, so, oh yeah, just now I left out, like what I said, at this point they are attract strongly by star B. Okay, so now let's come back to the question again. So when these two values are given, that means you have to calculate the change in kinetic energy from here to here. Okay, the change of kinetic energy from here to here. You have to know that this is the surface of star A, and at this point the rock reaches the surface of star B. Okay, so star A to star B. Okay, that means here to here. Okay, so now state whether this change is an increase or a decrease. So our main focus here is we want to calculate the change in the kinetic energy. So we have to use principle of conservation of energy. Okay, so that based on this graph, we can calculate the change in gravitational potential energy based on this formula. Let's look at the formula first. Okay, so of course this is the formula booklet. All the formula are here. Okay, so we have to use this formula. Number 13. Change in gravitational potential energy is m5 final minus m5 initial. Okay, so we calculate the change in gravitational potential energy first. The change in gravitational potential energy is very much related to the change in kinetic energy. I will explain that later, but let us calculate the change in gravitational potential energy first, as we can easily do that because the graph gives us the value of phi. Okay, so now let's take a look. Okay, so the formula that we are going to use, I write down first so that you're not so confused with so many things. So we are going to use this formula, m5 final minus m5 initial. Okay, so the mass here is the mass of the rock. Okay, it's the mass of the rock, which is 180 kg. 180 kg. So what is the phi final, the gravitational potential energy? So the phi final is here. Okay, you can see the red pointer, figure 1.2. Here, this is the final, this is the initial. So initially it is -10, and finally it is minus 14. Okay, so this is the phi final, this, whereas this is the phi initial. Okay, as the rock move from here, okay, move from here to here, that means we start from here to here. Okay, so this is the initial and this is the final. Okay, let us substitute into the formula. The final phi is -14. Don't forget there is a 10 to the power of 8 given in the vertical axis, so you have to put that into the calculations. Minus m phi initial minus 10 times 10 to the power of 8. Okay, so if you count this value, you will get minus 7.20 times 10 to the power of 10, and the unit is joule. Okay, so what is meant by this value? Okay, so you get a negative value. Okay, so meaning that you know we are calculating the delta U over here. The delta U over here is the change in gravitational potential energy. So if you get a negative value, that means this is a decrease in gravitational potential energy. Okay, so negative means that a decrease happens. So based on the principle of conservation of energy, when there is a decrease in gravitational potential energy, so that energy is changes to something else. It changes to kinetic energy over here. Okay, so it changes to kinetic energy. So I have to say that the decrease of gravitational potential energy makes the kinetic energy to increase. Okay, so that answered the question. So the change of kinetic energy is hence 7.20 times 10 to the power of 10 joule, which is the answer. Okay, and the other thing is they also ask, state whether this change is an increase or a decrease. So like what I explained, we have a decrease in gravitational potential energy, the energy is converted to kinetic energy. So there is an increase in kinetic energy now. So we have to answer increase. Okay, increase. So done for part 1. Okay, so now let's move on. Roman part 2. Okay, let's look at the question first. Roman part 2. At a point where x equal to 0.1 times 10 to the power of 12 meter. Okay, where is this point? Always remember that this point means it's on the surface of star A at here. You look at figure 1.1, is at here. The speed of the rock is v. Okay, the speed of the rock is v. That means this is the starting speed. The starting speed of rock is v. Determine the minimum speed v such that the rock reaches the point where x equal to 1.2 times 10 to the power of 12. Okay, so we have to know that 1.2 times 10 to the power of 12 is a point on star B. Okay, it's a point on star B. So what kind of minimum speed that is required by the rock so that it can reach star B? So you may understand it in this way. I give you one example. Imagine that a rocket a rocket on the earth which is planning to go to the outer space. So they need to overcome the gravitational attractions of the earth. So that's why the rocket need to move very fast. Need to move very fast to overcome the attractions, and then they can reach the outer space. Pass they can pass through the atmosphere and reach the outer space. Okay, so they need to overcome the attraction. So likewise, this rock, as you can see on figure 1.1, this rock need to overcome the attraction. You see the graph here, the attraction is kind of strong, it's -10, is kind of strong. Okay, the attraction is kind of strong. The rock need to overcome the attraction, so they need a particular speed. Of course, the faster the rock, the easier for it to overcome the gravitational attraction. But the thing is, they want minimum speed. Okay, minimum speed. We want a speed which is just enough to overcome the attraction of star A, and at the same time make the rock reaches star B. Okay, just enough to overcome the attraction. So how are we going to take it? Okay, so we have to take it in this way. We have to make use of the maximum point here. So the maximum point, which is somewhere around negative, if you can see, okay, hold on. Okay, so let's zoom a bit. If you can see it clearly, you should know that the maximum point of the graph is at the value of -4.4. Okay, so why this value is to be considered? Okay, so I have to say that this value is a point with the weakest attraction. Okay, I write down first. This point is the point with the weakest attractions by both stars. Okay, weakest attraction by both stars. So imagine, like what I said, when it's at the surface of star A, the rock is strongly attracted by star A. So when it's at the surface of star B, of course, based on the graph, is strongly attracted by star B. So there is a particular point in between where it is kind of far away from star A. The attraction by star A is kind of weak, and it's kind of far away from star B, so the attraction by star B is very weak. So it's that particular point. So why this point is to be discussed here, or why we need to care about this point. So imagine the rock need a particular speed to overcome the attraction by star A. The attraction by star A. So, and because of that speed, the rock can keep moving, and we just want the rock to reach this point. We just want the rock have just enough energy, just enough kinetic energy to reach this point. okay, and then after that, that will be enough already, okay, as long as the rock have just enough kinetic energy to reach here, then the rest we are not going to worry already, because the rock, once it once the rock can reach here, uh, it can reach star B, because as long as the rock can reach here, star B start to attract the rock and reach to the other side. So our main concern is we want to make the rock have just enough energy to reach here. Just enough energy to reach here. As long as it has that amount of kinetic energy, then the rest is handled by star B, and we are not going to care about that. Okay, so now let's come to the the question again. So in order to have just enough energy to reach here, we have to see how much how much change in gravitational potential energy from here to here. Okay, how much change in gravitational potential energy? So again, we are going to use delta U equal to m phi final minus m phi initial. Okay, so this time, uh, okay, I'm going to use blue color. Our m phi initial is here, and our m phi final is here. Okay, so as you can see in blue color, m phi initial, m phi final. We just want to make the rock to have just enough energy to reach this point, and we want to see how much change in gravitational potential energy over there, because change in gravitational potential energy is related to change in kinetic energy. Okay, so now let's substitute with value. Okay, so the n 180, the phi final is minus 4.4 times 10 to the power of 8 minus m. Phi initial is minus 10 times 10 to the power of 8. Okay, so if we count this value, you will get 1.008 times 10 to the power of 11 joule. So this time, the situation is we get a positive delta U. A positive delta U means there is an increase in gravitational potential energy. Okay, so gravitational potential energy increase. So that means that is a, based on principle of conservation of energy, when gravitational potential energy is increasing, that means the kinetic energy has to be decreasing. Okay, so this is reasonable, as you can imagine. Let's say the rock start with imagine rocket rocket initially very fast to overcome the attraction, then they are slowing down. Okay, so they are slowing down when they keep moving out. Okay, they are slowing down. Okay, so likewise the rock initially very fast. Okay, they need a particular speed, they need a particular speed which is fast enough to overcome the attraction of star A. So after that, it will decrease in speed, because of the attractive force which keep acting on the rock in the opposite directions of the motion. Okay, so it slowed down the rock. Okay, it slowed down the rock. So the idea here is, it slowed down the rock. It doesn't matter as long as the rock has just enough energy to reach this weakest point, then the rest is handled by star B, where star B can attract the rock and make the rock reach star B. Just enough energy. So means what? Means as long as the rock can reach here, uh, the minimum will be just enough until it stopped here will be the minimum. It stopped here. Okay, it stopped there. So okay, so it stopped there. That is the main idea. Okay, now I put in blue color again. So at this point the speed is v. At this point okay, the v initial is v, the v final is 0. That is just enough energy, you know. So final is 0, just enough energy. Okay, now let's come back to the questions. Okay, the change in gravitational potential energy is equal to the change in kinetic energy. Okay, now 1.008 times 10 to the power of 11, which is equal to, okay, so you have to know that I put it down here. The change in kinetic energy is equal to half mv, just take the big one minus the small one, you know. The big one is the initial minus the small one, which is final is 0, so that's why it's the small one. And you know that okay, maybe I put it here, half mvi square minus half mvf square. So substitute with value, half 180. So vi, right, is v. Okay, we need to look for that value is v. So final, you know, the vf, the final velocity is 0, so it makes the whole term turns to 0. Okay, so now we just need to solve these equations and find v. So we will get v square as 1.12 times 10 to the power of 9. We will get v as 3.35 times 10 to the power of 4 joule. Meter per second. Meter per second. This is velocity. Okay, so the unit is meter per second. ms -1. Okay, so this is the answer. So we have done the whole questions.